Hello, my name is Sophie Aerdker and I'm a PhD student at the Institute for Neurocomputation in Bochum. I will talk about our research on motor habituation and I will start with our experimental approach and later show you our theoretical model. So, starting with the terms of habituation and sensitization, they are a very simple form of learning, and in habituation, responses to a stimulus weaken across the repetition of the stimulus, and in sensitization, it's the other way around, so these responses would be strengthening. Habituation is widely used as a tool to study infant cognition, and when you want to do that, you could show a visual stimulus to an infant and measure its response, for instance, as looking time. So you stop the time when the infant looks away from the stimulus and then show the same stimulus again, and you will end up getting these profiles of looking time against stimulus repetition. And you will see that looking time decreases with the repetition until at some point you will stop presenting this boring stimulus to the infant, and this is typically when an habituation criterion is met, so the looking time falls below 50% of the average time you got on the first trials. Now you have habituation and you could present a new stimulus to the infant, and you will see that looking time is reinstated because habituation is always selective to a stimulus. This is called then dishabituation, and you can use the amount of habituation and dishabituation to assess infant perception and cognition, answering questions like how well do they discriminate between stimuli and do they recognize a stimulus. In the next step, you could then present the original stimulus again and see if responses are reinstated. And if they are, this is called Spencer-Thompson dishabituation, which is like a form of a long-term sensitization, because now you have a stronger response here than you had before on this trial. So this is a story how habituation is more used as a tool in infant research and not often as a research object on its own. Habituation is often used in the context of perception and cognition, and on the other hand, when we think about movement and movement generation, we think about habit formation or sensitization. And a well-known example is the A-not-B paradigm, first introduced by Piaget, where in the experimental procedure you hide the toy at two different locations. So for instance, you have a box with some lids you can cover the toy with, and you start hiding the toy under the A lid, and then push the box to the infants, and they will probably lift the A lid to get the toy. And then you repeat this procedure until the 7th trial, and now you hide the toy for the first time under the B lid. And again you push the box to the infant, and when they are about 10 months or younger, infants typically lift the A lid, even if they watched you hiding the toy under the B lid. So they perseverate in their movement, which is a form of sensitization. But as our title suggests, is there also habituation in motor behavior? And there's a hint by Markovic and colleagues who tested the influence of the number of A trials in this paradigm. And they found that when you have only one A trial, there's no perseveration at all, which makes sense because you have no repeated movement and so you have no sensitization. But they also found that when you have 11 A trials, infants were less likely to perseverate than in this traditional 6-trial condition. So this reduced perseveration may be due to habituation at a large amount of experience reaching to this A location. So A-not-B paradigm involves a selection decision, so it's not quite analogous to this habituation experiment I showed you before, where the time is measured after a decision to look at a stimulus was made. So to pinpoint this idea of habituation in motor behavior, we had to construct a task by using only a single motor task at a single location to get this really analogous to the traditional habituation paradigm. And this was done a couple of years ago in this experimental setup. So we had a box with a lever that could be moved only in one direction, and this box then played some music to make the movement all interesting and exciting for the toddlers. So we had a pretty boring environment. You see a lot of black in there to prevent visual distraction and also to prevent perceptual habituation going on there. and this box could be rotated to test the dishabituation to a new movement direction. We had 2 age groups, 38 12-month-old and 38 15-month-old, and we had 2 initial conditions, so they either started with the vertical or the horizontal movement direction. Every try lasted 15 seconds, then this box was pulled away from the toddlers on these tracks, and the moving time of this lever was recorded live, so this is really analogous to the looking time. And these are the results. This is the average movement time in the habituation phase for the first and the last trials. And you can see a nice habituation profile here until the criterion is met here. Then the box was rotated, and we see a significant dishabituation over the last habituation trial for all groups. And then we tested the Spencer-Thompson dishabituation to the initial orientation of the box, and we see that this is significant for some of these groups here. So this would be the comparison to the looking habituation paradigm, and our experiment indeed showed habituation to a movement direction. So when we now want to construct a theoretical model, it should account for the 3 things of habituation, dishabituation, and Spencer-Thompson dishabituation. And we will use the framework of dynamic field theory for that. There are previous process models on habituation in the looking paradigm and a model of first rate of reaching in the A0B paradigm using dynamic field theory. And our idea is to combine the habituation and sensitization in a unifying model, and then we want to see if this accounts for the data we have here. Okay. Now first, some background on dynamic field theory, where we have activation patterns of neural populations that are described as neural fields. And these fields are now spanned over the feature dimensions, so the dimensions the neurons are responsive to. And by this, field dimensions naturally are given by their connectivity to the sensory or to the motor surfaces. Now, this activation patterns somehow evolve in time, and this time evolution is described as a dynamical system. We have a forward connectivity from the sensory surfaces to other fields, and eventually to the motor surface as well. And we have also strong recurrent connectivity within the fields, which is really key in DFT because this gives us stabilized patterns or peaks of activation that are really robust against noise, robust against changing inputs. So let's take a look at our model. We have a one-dimensional field here over the dimension of the movement direction. And this field has the role of a planning field. So the movement generation is not explicitly modeled, but the intentions to move are modeled here. So we have no inputs to this field, and the activation it adds at the, we call it resting level. Now let's add some input to it. These inputs represent the experimental stimuli, but they are already processed in the way that they match our dimension of the field. Now this resulting peak represents then the intention to move, and in this case in horizontal direction. Now only field locations that are above a certain threshold engage in neural interaction and information is passed to other fields. And these field locations are stabilized against the decay by local excitation in the field, and they are stabilized against the diffusive spread by inhibitory connectivity. And these are mediated by some interneurons, some interpopulations that have this inhibitory connectivity. Now, when the activation passes the threshold, the dynamics change, and this is mathematically described as an instability. And I want to show you how that looks like on our webpage, where we have this nice simulator, and we again have this one-dimensional field, but now there's some noise in the field added to it. And when I now have an input here, you can see how the activation nicely follows the shape of the input. So this is an input-driven state. But as soon as the activation passes the threshold, we have this instability, And we have a local excitation and also inhibition here, which gives us the self-stabilized state. We may have various inputs in this field, but we also can have a field that is selective and only one peak at a time can emerge. And I would now need a really strong second input to change the decision of this field from the one to the other location. And this is how we model decision making in DFT by using instabilities. We have the detection instability that detects a significant input and then holds on to this decision. And this is how we may model the decision to look or not to look at the stimulus in DFT. And also we have the selection instability, so we can model to reach either to the A or to the B location in the A not B model. Okay, back to our actual model. We now add the second layer to the field, which has these inhibitory internuance that are responsible for later habituation. And this field gets input from the movement planning field, and once a peak forms here, it inhibits the movement planning field. So in this setup, the impact of this habituation field would not change across repetition, but the history of decisions in a field is crucial to get habituation and sensitization. So we need some form of memory, some form of learning to model that. And this is why we are laying down a memory trace at all locations of super-threshold activation in the field, and that decays at all other locations in the field. So here we have this one-dimensional field over our movement direction, and this is how it evolves in time. And you can already see the experimental procedure here. So we have multiple movements in horizontal direction, and then the switch to vertical and back to the horizontal. And here's the memory trace, and we can see that it builds up here with repeated movement in horizontal direction, and later it decays here, and when it decays here, it builds at the new movement direction, so at the new field location. This memory trace couples back to the movement field, so it facilitates peak formation, and by this it accounts for the habit formation in this field. So let's add these memory traces to our model, and we have one added to the movement planning field, and this facilitates now the peak formation here, so it is responsible for sensitization, and the second memory trace facilitates peak formation in this inhibitory layer, and by this it is responsible for this habituation profile. And this already is our full model, and I want to show you an example course of activation. These are the results we get when we implement this dynamical system in our MATLAB framework for numerical simulation. And you can see here the time evolution and the activation at the horizontal and at the vertical movement direction, so the field locations we are interested in. The experimental conditions are fully controlled by the strength and time duration of stimulus inputs to the movement planning field, which are these green boxes you can see here. We have a task input that indicates the movement direction, and also a rewarding and an attention input for the music that is playing, and also sometimes parents draw the toddler's attention to the box when they didn't move the lever spontaneously. And this task input lasted for about 15 seconds. And the activation in the movement planning field is this blue line here, and the activation in the habituation field is this red one here. And in each of these trials given by the task input, we counted the steps of super-threshold activation in the movement planning field, and this then gives us an approximation for the movement time that is actually going on in the experiment. And when we hit this habituation criterion, the task input switches to the opposite movement direction here, and this criterion is always met at different trials depending on the simulation, because we have some noise in our fields. Okay, now I can show you the important figure where we had 50 simulations with the same field conditions. We have the average approximated movement time in blue and the standard deviation in gray. And you can see this nice habituation profile here. Here's the criterion hit, and then the dishabituation here, and the Spencer-Thompson dishabituation, which is significant in some trials, but not in all simulations, as we have a really strong standard deviation here. So we didn't explore limits of this quantitative fitting, because again, we have this level of modeling the intentions to move and no explicit model of the movement generation. But what this shows is that with this simple pattern of only 2 neural fields and 2 memory traces and this varying inputs, we get this pattern of habituation, dishabituation, and sometimes the Spencer-Thompson dishabituation we saw in the experimental data. And with that, I want to conclude and give you like a take-home message. First, I showed you the experimental evidence of habituation in motor behavior. Then we had this idea of a unifying theory of habituation and sensitization to account for this experimental data. And in our model, we had habituation and sensitization as the buildup of activation in a neural field, which is described by these memory traces. And then we saw that this model actually showed habituation, dishabituation, and also the Spencer-Thompson dishabituation. Now, to give you a short outlook, there are also preferential looking tasks where you show 2 stimuli to infants, one that is always familiar and the other that is always new, so it's constantly changing during repetition. And when you now stop the time, you see that infants tend to look longer to the familiar stimulus early in this repetition, and they tend to look longer to the novel stimulus late across repetition. So this can also be described as a sensitization and a later habituation to this familiar stimulus. And this setup is because we have 2 stimuli is some way closer to the A0B paradigm, where we also suggested this sensitization and maybe a later habituation. But again, it's not quite the same, because in A0B we are measuring the decision, and in preferential looking we're measuring the time duration after a decision was made to look at a certain stimulus. Now, nevertheless, we tested this idea with our model by presenting a second input early or late during habituation phase, and we saw this pattern of an early familiarity and a late novelty preference in our model as well. So unfortunately, there's no experimental evidence so far. We only have a small pilot study with some hints to it, but still I want to end my talk with this question of whether there might be a universal pattern of an early familiarity and a late novelty preference, not only in perception, but also in motor behavior. And with this, I want to end. When you're further interested, let's take a look at our paper. I will show you my references, but I will quickly go back to my conclusion, because you can simply stop the video for that. And yeah, thank you for your attention, and I'm looking forward to your questions right now.